So can vertical planting with living walls mitigate the loss of urban green spaces? In the later presentation, I'll examine whether urban green infrastructure with such social and environmental ambition can be made effective and efficient technologically and economically. In this first presentation, I'll examine critically the claims for social environmental benefits of green walls. My aim is to stimulate further debate, development work and practical demonstrations. I want to thank the UCS and the University of Chester for this opportunity, and Dr. Jane Yardley in particular for her support. Over the last 2 decades, technologies have proliferated for creating gardens on buildings, both on the roof and the vertical surfaces. Every major city now has green wall installations, and this market continues to grow rapidly. The purpose of these installations is to provide a spectacular visual impact for mainly prestigious locations such as corporate headquarters, hotels, restaurants and shopping malls, where they support a corporate image or serve as a visitor attraction. Researchers are interested in the wider potential of green walls to contribute urban resilience to climate change and benefits to public health that are normally associated with conventional green space. There are 6 claims that I'll be reviewing from the scientific literature and adding some hopefully persuasive arguments of my own, which are as yet unpublished or independently reviewed. Similar arguments will apply to green roofs, which are more extensive, and hanging baskets and window boxes, which are seasonal decorative elements, also trellises that are ground-based planting systems. But my talks will focus on modular green wall planting systems, as these provide the greatest scope for benefits and are visually more accessible to the public. So how do I define a green wall? Well, green walls are a modular architectural surface element consisting of living plants growing in containers. These containers support growth of mostly evergreen plants for extended periods on vertical surfaces. They do this by providing a porous root substrate, which may be organic or inorganic material, and irrigation with a balanced mixture of plant nutrients. Modular systems provide scope for artistic expression through arrangements of the containers, producing planting designs with varying patterns, textures and colours. Planting designs are often either naturalistic or impressionistic in form. It's no coincidence that designs often draw inspiration explicitly from the Impressionist art movement, and related concepts such as the crisis of modernity, the loss of connection to rural life, and the associated unity between individuals that define and constitute a community. So let's look at the claimed environmental benefits. A climate change emergency has been declared following the consistent rise in mean global surface temperature. Many governments have committed to achieving net zero carbon in the next few decades, and buildings are a major culprit. In the US, for example, they account for 40% of the total carbon emissions and 74% of total electricity expenditure. 50% of this energy use is for space heating and cooling. Numerous trials have investigated the effects of living walls on buildings' thermal efficiency. Typically, thermal sensors may be placed along the path of heat transfer, and the measurements used to calibrate a computer model that simulates the heat flow, which is then used predictively. The illustrated example is from Wuhan in China, Others have been performed elsewhere, often in Mediterranean climates. Thermal damping is observed in temperature readings from the interior surface and the interior space. The dark shaded line shows the green wall effect over a 24-hour period. The light shaded line shows the larger fluctuating temperature with a bare wall. Green walls are known to contribute to thermal efficiency of buildings in 4 different ways. They are solar reflectivity or shading, latent heat of evaporation from the foliage, thermal mass dampening of the substrate or insulation from the structure, and wind shelter. Energy savings vary between 5 and 50%. A study in Athens reported heat energy savings of 10% and cooling energy savings of 4%. A life cycle analysis in the US estimated a 3-year payback of energy used in manufacture. A related thermal problem is the heat island effect, which is where air temperature over a city is often higher than that of the adjacent rural area. The cause is solar radiation being absorbed by building materials and then transferred as heat to the surrounding air above the city. The result is increased load on air conditioners and increased discomfort for city residents, as well as health consequences and a greater threat from climate change. Vegetated buildings can reduce the heat island effects. For example, a London case study showed that ambient air temperature in front of a green wall was reduced by between 0.5 and 4.1 degrees centigrade compared to a distance of 2 meters away. But citywide effects can only be assessed by simulation modelling. One such study showed that air temperature above a vegetated roof could be 10 degrees centigrade cooler than the same roof covered by a reflective white surface. But on a city scale, it would require more than half the roofs to be vegetated just to achieve a 1 degree centigrade drop in air temperature. And the temperature at ground level is only slightly affected by vegetation on the roof. But combined with a green wall, the maximum day temperature could be potentially decreased by 34%, compared with 14% for green walls alone. In conclusion, vegetation can improve a building's thermal efficiency, also its local thermal environment, but there are many local variables to consider, which may require complex thermal analysis and expertise in dynamic simulation modelling. Thermal inefficiency affects lower income and marginalised communities the most, and older properties account for the great majority of buildings, where much can be achieved using standard improvements to thermal insulation, and for new properties with better materials and designs. Yet there remain formidable barriers. These include the property market, competition and uncertainty. The main requirement is for regulatory incentives that favour selection of vegetation methods and technical development to establish the methods with associated design tools that make vegetation options easier to evaluate and to implement. Exposure to acoustic noise causes annoyance and sleep disturbance, with negative effects on the cardiovascular and metabolic systems and cognitive impairment in children. WHO estimate that these health effects cause the loss of 1 million healthy years of life every year. Noise caused by transport is considered the second most significant environmental cause of ill health in Western Europe. That's behind fine particulate matter air pollution. High levels of road traffic noise affects at least 20% of the population during the day and 5% during the night. And in wildlife, communication and reproduction are also badly affected. Noise barriers and sound insulation are some of the measures used for reducing the effect of noise in the built environment. They may be a co-benefit with measures used for air pollution, which is discussed later. The sound absorption property of a green wall is better than most materials commonly used on the facade of buildings, particularly at the low end of the sound frequency spectrum. Only a few detailed studies of green wall acoustic properties have been reported, and they show variable acoustic gains. In this example, a geotextile planting module was tested in a reverberation chamber. The results showed a significant reduction in reverberation time along the analysed frequency range, but there was no appreciable effect on sound insulation. Another study tested the acoustic performance of a single vegetated wall at street level. It provided a moderate noise reduction, which was attributed to the acoustic absorption by the planting substrate. Many other studies have shown the acoustic effect of plant foliage is minimal and mainly consists of scattering higher frequency sounds. So in conclusion, plant panels have potential as sound absorbers equivalent to acoustic elements, but only in consequence of the various configuration possibilities of the panels and the materials that compose them. Air pollution derived from fossil fuel combustion causes and worsens respiratory disorders. In 2011, it was estimated to cause 400,000 premature deaths in Europe. Recently, it was blamed for 8 million premature deaths worldwide. The economic impacts of treating respiratory illness are also highly significant. The chief cause of air pollution in cities is vehicle exhaust plumes. One of the most dangerous components is nitrogen dioxide, which is subject to statutory limits for exposure, but these are regularly exceeded. Another major component is microscopic particle matter, known as PM2.5, which is only subject to guidelines. In the UK, roadside levels of these pollutants are declining due to vehicle improvements, but eliminating the pollution source at every vulnerable location might not be achieved for decades. So some means is needed to protect vulnerable members of the public from exposure to toxic fumes that are concentrated at pollution hotspots. Roadside acoustic barriers can increase air turbulence, which helps disperse plumes of vehicle exhausts. But this depends on meteorological conditions and local topography, so the results are difficult to predict and very variable. Vegetation canopies provide further possibilities for capturing microscopic particles that are deposited on the leaf surface. Also nitrogen dioxide, which is absorbed through stomatal pores in the leaf and metabolized by the plant. Researchers at the universities of Birmingham and Lancaster adapted a fluid model to simulate the effects of air mixing and deposition of pollutants in the street canyon. In conditions of low wind speed and a vegetated wall covering approaching 100%, their results suggested nitrogen dioxide and microscopic particles could be reduced possibly by as much as 35 and 50% respectively. However, the established view is that any filtration method would be impractical, because the required rate of airflow over the filter would have to be prohibitively high. It would never be possible to filter all the sky above a polluted city, which seems a compelling argument. But I can envisage a scenario that would remove the requirement to filter a large proportion of the air. It covers the worst air quality problem that can occur where the ventilation of plumes from heavy, slow traffic flows are impeded by the street topography. In this scenario, children are particularly vulnerable due to their small stature, which places them close to the pollution source emitted directly from the vehicle tailpipe. My proposal would place a barrier at the edge of the pavement between the pedestrian and the source of the emissions. This barrier would serve both to filter and to disperse the emissions at the point where they are most concentrated and accessible to small children. My idea goes further by providing a means to increase filtration rates by several orders of magnitude. This would be achieved by including, for the first time, additional pathways for the deposition of nitrogen dioxide and microscopic particles. These pathways are the plant root system, the root substrate, and the irrigation system, as well as the plant canopy. I can also envisage benign amendments to the irrigation supply that would react chemically with nitrogen dioxide to help achieve the higher deposition rates. And I've developed a deposition theory that would enable predictive modelling for such a system. For those interested in the equations, the first is a standard equation for dry deposition to a water surface, and the second is for radial flow to the root surface. The proposed parameters are measurable through experiment and allow testing of the theory with independent data sets. If shown to be valid, the parameters could be incorporated into a predictive model that would help in the design of better pollution filters and to test different scenarios. Biodiversity is an urgent global problem. Studies estimate that billions of animal populations have been lost in recent decades. The cause is due to habitat destruction, overhunting, toxic pollution, invasion by alien species, and climate change, which are all linked to human population growth and overconsumption. Urban biodiversity is a continuing topic of debate. Urbanized land only occupies 3% of the land surface area. Species of plants and animals represented in urban landscapes tend to reflect those in surrounding areas, but also include many introduced species. Urban landscapes might be considered biodiverse in terms of species richness, but biodiversity can be considered at several levels, including genes, individual species, communities, and entire ecosystems. Understanding how ecological processes function in cities has become important for conserving biodiversity. The key areas identified are the green space size, animal life cycle requirements, dependence on heterogeneity, and connectedness of the green spaces. Green walls and roofs provide habitats and food for wildlife, and green walls can be surprisingly biodiverse. The potential pitfalls are the creation of population sinks, which is where animal reproduction and survival rates are unable to sustain a population due to a low quality habitat. Also ecological traps, which is where an animal selects a sink habitat in preference to an available higher quality habitat. Restoring built environments for biodiversity looks promising, particularly where it involves citizen participation. There's considerable potential in using green walls to enhance biodiversity. In principle, green walls can be engineered to include physical complexity, species assemblages, and dynamic environmental controls that mimic a specific natural habitat. Ecologists might consider the possibilities, which would seem endless, in collaborating to engineer green wall solutions for specific biodiversity goals. In the meantime, a key benefit of vertical planting might be in exposing city residents to wildlife and promoting an emotional bond to nature. Natural environments produce relief from mental stress, even with short-term visits to nature. This observation is supported by an abundance of scientific evidence. Even exposure to views of nature can improve health and reduce mental fatigue, reducing levels of the stress hormone cortisol measured in saliva. Access to nature reduced mortality from circulatory diseases, increased survival rates of urban senior citizens, improved feelings of neighbourhood safety, and decreased aggression and crime rates. The biophilic architecture movement is based on the premise that there's an innate genetic human preference for natural habitats, and has attempted to codify the key architectural elements, including the use of greenery, which they link to a supposed human ancestral homeland with a savanna-type landscape. This idea seems untestable. Most aesthetic choices, perhaps all, can be shown to be culturally acquired or learned. The recent discovery of fractal geometry is appealing because of the ubiquity of fractal patterns that occur at every geometric scale in the universe. All animals that use vision must quickly learn to make sense of their visionary landscape from the two-dimensional images that are focused on the retina at the back of the eye. It's conceivable that fractal organization of nature can minimize the brain's work in processing and making inferences that are essential for survival in the wild, which could also account for mental stress or fatigue that occurs in man-made urban landscapes that tend to be deficient in fractal patterns. Another positive role for green walls is likely to be place attachment, which is the concept that positive human bonds can be formed to social and physical settings that support identity and provide other psychological benefits. Green walls blur the boundaries between the natural and the built environment and may serve an important function in urban design by providing porosity between the public and private space. Boundaries termed transitional edges are a key concept in the emerging field of socially restorative urbanism. Transitional edges reside at the boundary between the built fabric and the adjacent open space, which is where people have a tendency to congregate, and precisely the location where green walls tend to be installed. The discipline of socially restorative urbanism provides practical tools for dealing with issues of local empowerment, community preferences, and providing a voice to the normally voiceless in society, and also the role of professional inputs and resources. My conclusion to this talk is that there is considerable evidence for the positive effects of green walls in each of the 6 areas claimed, but in each case there are technical alternatives that are likely to be equal or superior in performance. One exception perhaps is the most obvious and least studied benefit, which is the aesthetic improvement of densely built urban environments. I would argue that there is a requirement for technical developments that increase the scope for artistic expression through choice of plant species, planting designs, and seasonal flexibility, and that in combination the effects of green walls can provide benefits for urban health and well-being that are potentially immense. And I would include another benefit, which is the economic regeneration from a new green supply chain that is replicable in every city and conurbation, with employment prospects in design, manufacture, materials, installation and maintenance. In my next presentation, I'll deal with the chief constraints that are due to doubts about the technical effectiveness and economic efficiency of current planting systems. In the remaining period of this presentation, I'll be happy to address any questions or points you might care to make. Thank you.